So now here we are going to talk about different types of ordinary differential equations and how to solve them. So basically there are four types of ordinary differential equations. Number one, variable separable differential equation. Number two, homogeneous differential equations. Number three, linear differential equations. And number four, exact differential equations. Now we will discuss each type of these ordinary differential equation and the method to solve them in details one by one. So today in this video we are going to talk about variable separable differential equations. So what is a variable separable differential equation? A differential equation which can be written in the form fy dy is equal to phi x dx. Any differential equation which can be written in the form fy dy is equal to phi x dx. That is, if it is possible in a differential equation that we may transpose all the terms having y and the operator dy on one side of equality and all the terms having x and operator dx on the other side of equality, then the equation is said to be a variable separable differential equation. For example, if differential equation is given as x plus 1 dy upon dx is equal to x bracket y square plus 1, so clearly we may transpose y square plus 1 to left hand side and x plus 1 and dx operator on the right hand side. So we may write it as 1 upon y square plus 1, because on transposition it will go in the denominator. So 1 upon y square plus 1 dy is equal to, and we transpose x plus 1 and operator dx to right hand side. So this x plus 1 goes in the denominator of x. So we have x upon x plus 1 and dx operator in the numerator. So doing so, we have written this equation in the form fy dy is equal to phi x dx. Fy means some function of y with operator dy, phi x that is some function of x with operator dx. So here 1 upon y square plus 1 is fy, that is some function of y with operator dy, and on the right hand side x upon x plus 1 is a function of x and dx is the operator. So this is the form fy dy is equal to phi x dx. So any equation which may be written in this form is known as variable separable differential equation. Now let's talk about how to solve a variable separable differential equation. Step 1. A variable separable differential equation is written in the form of fy dy is equal to phi x dx if it is not given in the above form. That is, first if we observe that the given differential equation is variable separable differential equation, so first we have to observe whether it is written in the form fy dy is equal to phi x dx, and if it is not written in this form, first we have to write the differential equation in this form, transposing all the terms of y and or y dy operator on left hand side and transposing all the terms of x and dx operator on the right hand side. If the differential equation is given right in this form, so the first step should be skipped. Now step 2. After rewriting variable separable differential equation in this form, we simply integrate both sides of the equation, integrate both sides. So we get integral fy dy is equal to integral phi x dx. So after integration, we get some solution of the sort hy is equal to gx plus c, where c is the constant of integration. Now if some boundary value condition is also given, like then using this boundary value condition, we need to find the value of c also. Then we substitute that obtained value of c in this equation. If the boundary value condition is not given, then this sort of solution is called general solution. And if we find the value of c with the help of some boundary value condition and substitute the value of c, then that is called particular solution. For example, bracket xy square plus x dx plus bracket yx square plus y dy is equal to 0 is the differential equation which is to be solved. So as we observe, the x out of this bracket may be taken common. So we get x inside the bracket, we are left with y square plus 1 dx. In the same way, from the second bracket, we may take y common, leaving x square plus 1 inside the bracket, dy is equal to 0. Now, transposing this term to right hand side, we get on the left hand side only this term, y x square plus 1 dy is equal to, on transposition this term, it becomes negative minus x y square plus 1 dx. Now we have to transpose x square plus 1 to right hand side and y square plus 1 to left hand side. So we get y upon y square plus 1 dy is equal to, transposing x square plus 1 to right hand side, we get minus x upon x square plus 1 dx. In this way, we have written the given differential equation which was not in the standard form, in the standard form as fy dy is equal to phi x dx. This is fy dy and this is phi x and dx. So this is standard form. After that, in the second step, we need to integrate both sides. So integrating both sides, we get integral y upon y square plus 1 dy is equal to minus integral x upon x square plus 1 dx. Now it is better to multiply both sides by 2 because if we multiply both sides by 2, here we will have 2y and here we will have 2x. And as you know well, the differential of y square plus 1 is exactly 2y and differential coefficient of x square plus 1 is exactly 2x. So this is not mandatory to multiply both sides by 2, but if we multiply by 2, this is better. So we may multiply by 2. So in the numerator we have 2y upon y square plus 1 dy. On the right hand side, minus integral 2x upon x square plus 1 dx. Now simply this is the case of substitution, integration by substitution. So we assume y square plus 1 as u and x square plus 1 as v. So differentiating equation, say this is equation 1 and say this is equation 2. So differentiating this equation with respect to u, we have 2y dy upon du. Differential coefficient of 1 is 0, as you know well, and differential coefficient of u with respect to u is 1, or transposing du to that side, we get 2y dy is equal to du. In the same way, differentiating equation number 2 with respect to v, we get 2x dx upon dv. Differential coefficient of 1 is 0 and is equal to differential coefficient of v with respect to v is 1. Transposing dv to that side, we get 2x dx is equal to dv. In the left hand side, in the integration, 2y dy is there, so we may replace 2y dy by du on the left hand side, and we may replace 2x dx by dv on the right hand side. So by these two substitutions, this equation turns out to be integral 1 upon u du, because we have to replace y square plus 1 as u, because we have assumed y square plus 1 as u, and 2y dy is equal to du, so this is equivalent to du. So simply integral 1 upon u du is equal to minus integral, and we have substituted x square plus 1 as v, so it becomes v, and 2x dx is equivalent to dv, so it becomes 1 upon v dv. Now, as you know well, simply the integral of 1 upon u du is log u is equal to minus integral of 1 upon v is log v, and after integration, if we get all the terms of the equation in the same format, whether it is logarithmic or exponential or some trigonometric, so constant term should also be taken in the same formats, though it is not mandatory, but it is better to take in the same format. So log u is equal to minus log v, that's why we have taken constant term also in the form of log, that is log c. Now simplifying this, we have to transpose log v to left hand side, so we get log u plus log v is equal to log c. And by logarithmic law, log m plus log n is equal to log m into n, so log u plus log v becomes log u into v. So log u into v is equal to log c. If on both sides of equation log is there, so we may compare these two expressions, so it implies that uv is equal to c. So after that, no further simplification is left, and when we reach at this point when no further simplification is left, then we have to write u and v back in terms of x and y according to our substitution. So we have substituted y square plus 1 as u, so we have to write u y square plus 1 back, so it implies that y square plus 1 in place of u, and we had assumed x square plus 1 is equal to v, so we have to write v as x square plus 1, so bracket x square plus 1 is equal to c, and this is the required solution of the given differential equation. Now let's take another example. X dy upon dx plus cot y is equal to 0, and given that y under root 2 is equal to pi by 4, that is boundary value condition. So x dy upon dx plus cot y is equal to 0. First we have to transpose cot y to right hand side, we get x dy upon dx is equal to minus cot y. Now transposing cot y to left hand side and x and dx operator to right hand side, we get 1 upon cot y dy is equal to minus 1 upon x dx. As we know, 1 upon cot y becomes 10y because the cot is reciprocal of 10, so we may write it as 10y dy is equal to minus 1 over x dx. Now this is in standard form, fy dy is equal to phi x dx, so Next step is to integrate both sides of this equation. So in integrating, so we get integral tan y dy is equal to minus integral 1 upon x dx. So integral of tan y is log sec y, log sec y is equal to minus, and integral of 1 upon x is log x, so log x. And since both the terms are in the form of log, so constant term should also be taken as log c. Now transposing log x to left hand side, we get log x plus log sec y is equal to log c. Using logarithmic law, log m plus log n is equal to log m into n, we may write it as log x into sec y is equal to log c. So it implies that comparing these two expressions, we get x sec y is equal to c. This is general solution, but since the boundary value condition is given with the differential equation in the sum, so we need to find the particular solution, that is, we need to find the value of c also for this boundary value condition. So now we have to apply this boundary value condition in order to find the value of c. So boundary value condition is given y under root 2 is equal to pi by 4. It implies that this is the value of x and this is the value of y. If it is written like y something is equal to something, so this value indicates the value of x and this value indicates the value of y. So x is equal to under root 2 and y is equal to pi by 4. These two values we need to substitute in equation number 1. So in place of x we write under root 2 and in place of y we write pi by 4. So sec pi by 4 is equal to c, or under root 2 as it is, in sec pi by 4, that is sec 45 is under root 2 is equal to c as it is. So it implies that under root 2 into under root 2 becomes 2, so we get c is equal to 2. Let it be equation number 2. Now we need to substitute this value of c in equation number 1, which gives us the required solution of the given differential equation. So from 1 and 2, we get x sec y is equal to 2, which is the required solution of the given differential equation. Now example 3 is sec square x tan y dx plus sec square y tan x dy is equal to 0. So obviously this is not given in the standard form, that is f y dy is equal to phi x dx. So first step, we need to write this equation in the form f y dy is equal to phi x dx. First we have to transpose this expression to right hand side, so only this term is left on left hand side. Sec square y into tan x dy is equal to, on transposition of this term it becomes negative, minus sec square x tan y dx. Keeping sec square y dy on the left hand side, we have to transpose tan y to left hand side, so it goes in the denominator. So sec square y upon tan y, and dy operator is also kept on left hand side. On the right hand side, if we have transposed tan y to left hand side, there is left minus sec square x dx, and we have to transpose tan x from left hand side to right hand side, so it goes in the denominator. So it becomes minus sec square x upon tan x dx. This is exactly the same format as fy dy is equal to phi x dx. So next step is to integrate both sides. So integrating both sides, integral sec square y upon 10y dy is equal to minus integral sec square x upon 10x dx. Now it's quite clear this is a case of substitution, because differential coefficient of 10y exactly sec square y, and on the right hand side also this is a case of substitution because differential coefficient of 10x is exactly equal to sec square x. So we have to assume 10y as u, let it be equation number 1, and 10x is equal to v, let it be equation number 2. Now first we have to differentiate equation number 1 with respect to u. We get sec square y dy is equal to du, and differentiating equation number 2 with respect to v, we get sec square x dx is equal to dv. So now if we apply this substitution on left hand side and this substitution on right hand side, our equation becomes 1 upon u du, because we have replaced 10y by u according to this substitution, and according to this substitution sec square y dy is equivalent to du. So we have replaced sec square y dy by du. So we have integral 1 upon u du. In the same way on the right hand side we get minus integral 1 upon v dv. So integral of 1 upon u with respect to u is log u is equal to minus integral of 1 upon v is log v, plus constant term should be taken as log c. Transposing log v to left hand side, we get log u plus log v is equal to log c. Log u plus log v becomes log u into v is equal to log c as it is. So it implies that uv is equal to c. So let it be equation number 3. So no further simplification is possible now. So at this point of solution, we need to substitute the value of u and v back in terms of x and y according to our substitution. So according to our substitution, u was 10y. So here we have to replace u by 10y. And from equation number 2, v is equal to 10x. So here we have to replace v by 10x is equal to c. And that's it. This is the solution of the given differential equation. Now let's take example number 4, which is bracket e raised to the power y plus 2 sin x dx minus e raised to the power y cos x dy is equal to 0. So obviously this is also not in the standard form. So first we have to rewrite in the form of fy dy is equal to phi x dx. E raised to the power y plus 2 sin x dx minus e raised to the power y cos x dy is equal to 0. This is given in differential equation. So first we have to transpose this term to right hand side, leaving this on left hand side, minus e raised to the power y cos x dy is equal to minus e raised to the power y plus 2 sin x dx. We have to transpose cos x to right hand side and e raised to the power y plus 2 bracket to left hand side. So transposing this bracket to left hand side, we get minus e raised to the power y upon e raised to the power y plus 2 dy, and transposing cos x to right hand side, we get minus sin x upon cos x dx. Obviously both sides have same signs, negative, so these two minuses are cancelled with each other. We are left with the standard form fy dy is equal to phi x dx, or we may simply write it as 10x. So one more step, e raised to the power y bracket e raised to the power y plus 2 dy is equal to 10x dx. So now integrating both sides, integral e raised to the power y upon bracket e raised to the power y plus 2 dy is equal to integral 10x dx. So now clearly this is the case of substitution, because if we assume e raised to power y plus 2 as u, differential of this expression is exactly e raised to the power y. So we have to assume e raised to the power y plus 2 as u, and differentiating this with respect to u, we get e raised to the power y differential is e raised to the power y dy upon du with respect to u, and a differential coefficient of 2 is 0, so there is no need to write it. And on the right hand side, differential coefficient of u with respect to u is 1, so transposing du to that side, we get e raised to the power y dy is equal to du. Now there is no need to substitute anything on the right hand side because this is integrable directly. So by this substitution, this side, left hand side, becomes 1 upon u du, because we have assumed e raised to the power y plus 2 as u, so here we write only u, and by this substitution we have e raised to the power y dy is equal to du. So in place of e raised to the power y dy, we have written du. So we have integral 1 upon u du is equal to integral 10x dx. Now integral of 1 upon u is log u, and integral of 10x is log sec x plus log c. We may apply log m plus log n as log m into n, so we may write it as log sec x into c. So it implies that u is equal to sec x into c. Now we have to transport sec x to left hand side, so it becomes u upon sec x is equal to c, or 1 upon sec x may be written as cos x, so we may write u cos x is equal to c. But we don't leave the answer in terms of u or v, that means in terms of variable which we have assumed. So we have to write it down in terms of x and y. So finally in the last step we have to write u as e raised to the power y plus 2, because that was our initial assumption. So replacing u by e raised to the power y plus 2, we get e raised to the power y plus 2 into cos x is equal to c, and this is our required solution of the given differential equation. Now the next example is example number 5. dy upon dx is equal to e raised to the power x minus y plus x square e raised to the power minus y. dy upon dx is equal to, by theory of indices, we may write e raised to the power x minus y as e raised to the power x into e raised to the power minus y plus x square e raised to the power minus y as it is. So dy upon dx is equal to, from both these terms, clearly e raised to power minus y is common, so we may take e raised to power minus y common. Inside the bracket we are left with e raised to power x plus x square. Now we have to transpose e raised to the power minus y to left hand side and dx to right hand side. We have 1 upon e raised to the power minus y dy is equal to e raised to the power x plus x square dx. Since 1 upon e raised to the power minus y may be written as e raised to the power y, so it becomes e raised to the power y dy is equal to bracket e raised to the power x plus x square dx. Now it is exactly in the standard format fy dy is equal to phi x dx. So now in the next step we have to integrate both the sides. So integrating both sides. Integral e raised to the power y dy is equal to integral e raised to the power x plus x square dx. So integral of e raised to power y with respect to y is e raised to the power y is equal to, and integral of e raised to power x with respect to x is e raised to the power x, and integral of x square is x cube upon 3 plus c. So e raised to the power y is equal to e raised to the power x plus x cube upon 3 plus c is the required solution of the given differential equation.